Uh, Hello everyone. Good evening from Japan. So today is our weekly seminars for Pakistan Catalyst Society, and I'm Muhammad Asif, a researcher and founder for Pakistan Catalyst Society, and I will be your host for this evening. So basically, this is our repetitive session that supposed to be held in the last week, but due to some internet problems, so we are repeating this seminar today. And I'm very thankful to the audience and the participant for understanding the situation and joining us for the seminar. Today, we are honored to have Mr. Nasir Ali Khan. His current research interest is on electrocatalytic carbon dioxide reductions. And today, he will be presenting an overview of the conference that held in the Wuhan city of the China. And the title of the conference was Carbon Dioxide Conversion by Renewable Energy. So after this presentation, there will be another session for the questions and answers. So you all can prepare your answer and you may write in the chat box or you can raise your hand and a chance will be provided to you to speak and to ask a question directly and you have a discussion with the speakers. So today's speaker, Mr. Nasir Ali Khan, please, you are welcome for this presentation and please you can start. Thank you.
Hello everyone. I'm Nasir Ali Khan. I'm doing my PhD in Environmental Science and Engineering from Beijing Forest University. Uh, uh, I'm very thankful to Mr. Muhammad Asif, founder and patron chief, and Mr. Muhammad Lukman Hakim, president of Pakistan Catalysis Society, for providing me an opportunity to serve as a vice president and secretary general of Pakistan Catalysis Society. Uh, I would like to present last attended conference, which was held in the Wuhan city, arranged by Wuhan University of Technology. So let's go to the main topic, that what I have done, and I would like to share some insights which I have done over there. So let's come to the topic. Conference was arranged by Wuhan University of Technology, which the main topic was CO2 conversion by renewable energy. There are different kind of conversion processes, but especially I would talk about the electrocatalytic reduction of CO2 and converting to different kind of renewable energies. So there was great speakers were there and great researcher. I met them. I have gained a lot of uh, a lot of knowledge were there. Some of the key speakers I would like to present their work and what's going on currently. So one of the professor from University of Australia, Yan Jiao. She is a professor in chemical engineering. Her recent work, molecular modeling of electrocatalyst and electrolyte for CO2 reduction reaction. So she was thinking about that. Electrocatalysis is basically on the base of electrolyte, and electrocatalysis should be the electrolyte should be considered during this reaction. So main work was on the electrolyte, that how we can molecular modeling electrocatalysis and electrolyte, and then we can get great periodic efficiency of CO2 reduction reaction. The second speaker, she was the professor in Xinjiang University. Her name is Jing Yu. Recent work is advancing and sustainability engineering strategies for efficient CO2 electrochemical reduction, that how we can advancing the strategies, engineering strategies, just like doping engineering, electrolyte, the reactor engineering, and different kind of engineering, we can improve the electrochemical reduction of CO2. And the third speaker, Yeonjun Hwang, Seoul University, South Korea. Uh, she is associate professor in the Department of Chemistry at Seoul National University since 2021. Her recent work was dynamic shifts, how electrolytes influence the product selectivity and CO2 electroreduction. As we know that electrolytes have a very basic function and the electrolytic reduction of CO2. So I would like to share some of the detailed presentation of other professors, which I have a great interest in that areas. So another key speaker, Anthony Suji Hall, he's assistant professor in the Department of Material Science and Engineering at the John Hopkins University. And his recent work he presented during the conference was promote CO2 emission by tuning the interfacial dynamics to that how can be electrochemical reduction influentially interfacial dynamics of H2O, that how can it will affect the when we are changing the structure of water, that how it will be affect the process. So basically, he's talking about that there are mainly two strategies. That one is the material design, that how we can design the catalyst for the reduction process, that how we can make it improve. Another one is electrode microenvironment. As we know that electrode microenvironment have a very has a lot of contribution to the electrocatalytic reduction. So electrode microenvironment have different factors: salvation, ion pairing, water activity, reaction plane, transport, and transition state stabilization. But basically, he was working on the water activity, that if we are changing the water activity, how the electrochemical reduction will be changed. So here's some key points uh, he was thinking about, that this is the paper which was published in 2015. Electrochemical CO2 reduction may be proton dependent. This was a hypothesis based on pH dependent experiment conducted by Oyori late 18th century. However, water serving as a potent proton donor, high cell concentration lower the activity of water. So he also analyzed the cell concentration and activity of water, and then how it will affect the electrochemical reduction of CO2. Water salvated by ion pairing, and decrease water concentration lower the activity of water. So another paper he presented over there, which was published in 2023 in Nature Catalysis. The main theme of this paper was water activity is the main parameter where at high salt concentration. Lower the water activity promote the formation of C2 products. If we are tuning the H2O activity control completion by adsorbate, so the product will be changed. For example, here he presents some of water activities. If the water activity is high, so it's mean the fissile water dissociation. So the H2 evaluation will be increases. It means the hydrogen production will be increases. And the second one, carbon one formation will be increased. For example, carbon monoxide will be increases, but CO2 product formation will be decreases. If we lower the water activity, if we suppress the water dissociation, so the hydrogen evaluation and the hydrogen production will be decreases, and carbon one, C1 product formation will be also decreases. But our main theme is to increase the C2 product formation. So if we increase decreasing the water activity, the C2 product formation will be increases. The hypothesis lower water activity promotes higher CO coverage. So in recent work, He worked on the water activity that if we are increasing or decreasing the soil concentration, that it will affect the water activity and how it alternately it will affect the CO2 reduction formation, CO2 or CO1 or long chain, short chain. So as the NaClO4 concentration increases, we can see here product distribution, fatigue efficiency shift possibly due to a change of water structure or ion pairing effect. He also present the water how the water structure is being changing with increasing the salt concentration. But there were a lot of snaps, so I didn't add that snap over here. The current density also increases, as we can see in the figure, indicating that higher NaClO4 concentration enhances overall reaction rate but affect the product selectivity. So our main focus should be on the product selectivity, that which kind of product we need and which kind of product we are targeted. So from the graph, the second graph, you can see the ferritic efficiency and NaCl concentration. Uh, if the concentration is lower, the concentration of the salt is lower, so the H2, the hydrogen production is increases, and C2H4 little bit decreases. But if the concentration is increasing, the H2O is decreasing and the CO2 product is increasing. So another key speaker, Thomas Borne, he is an associate professor in chemical engineering at the Delft University of Technology in Netherlands. His recent work I would like to present here: design efficient, selective, stable, and scalable CO2 electrolyzer for carbon monoxide in ethylene production. So, as we know, a huge progress made in CORR selectivity towards one single chemical over the past decades. So he was thinking that it should be a catalyst design, reactor engineering, and microenvironment manipulation, as I discussed before, before that only two factors, catalyst design and microenvironment manipulation, will be affect the CO2 reduction. But he added another thing. Reactor engineering is also important thing. So he quote some of the ferritic efficiency in the previous literature, that 100% for CO and format, 90% for ethylene, 40% for ethanol at a few hundreds of current. So prophenol is still only a few examples, but we can improve the catalyst design, we can improve the reactor engineering, and we can improve the microenvironment. There are a little bit we can improve, and we can get good selectivity and good efficiency. So how we can increase these things? Understand and propose solution to cover reconstruction for long-term operation of CO electrolyzer. So if we can see in the first figure, initial copper, we can see in the same image, and then after 10 hours, the structure of the copper is a little bit destroyed. And the second one, the graph, which they will compare some with the timing operating, that how can be timely affect the site the structure of the catalyst. So for the ethylene selectivity, here after 100 hours, the copper is completely wall updated. So we need further, if we want to be commercialized, or if we need to industrialize, so we need to stabilize the catalyst for 40,000 to 60,000 hours. Then we can make it commercialized or something like that. And another, why making well-defined nanoclusters if a catalyst change during operation. Well-defined NCs are an ideal platform to understand the mechanism behind the transformation, so that we can propose solution and move forward. And another same picture we can see before, after some time, the nanocluster changes their structure. After 3 hours, the structure is more a little bit destroyed and more substantial changes emerging after 3 hours. We can see here. So and then he analyzed also on the basis of 3D electron tomography that how the structure of the catalyst will be changes with the time and how we can stabilize this structure. Then another strategy, he was thinking that maybe it will work, and this paper is also published in the Nature Material. Functional coating to boost the copper stability during CO2 double R. Electron conduction, mechanical stability and porosity for gas diffusion, beneficial electronic interaction, tunable synthetic route. Then he was thinking that maybe if we are covering the structure of the copper with another material to increase the stability, so it is also a kind of way that we can improve the stability. The hybrid alumina coating hinders copper reconstruction and enhances the operational stability. One side, alumina increases the copper, operational stability, but in another side, it hinders the copper reconstruction. So it's not a good way. So another picture we can see here, material chemistry strategy to stabilize copper electro catalyst. That what kind of way we can improve the stability. So compositional tuning, one way, and another way we can coat the material or regeneration or reconstructing. Time to learn how to direct both stability and selectivity to combine these material strategies with system level strategy and develop accelerated stability test. Uh, Here another PhD student. She also talking about the structure of the catalyst as well as with various pH, that if we are increasing the pH, what will happen to the catalyst and what will happen to the ferritic efficiency. From figure 1 we can see that nickel nitrogen carbide showed almost 100% of carbon monoxide ferritic efficiency in various pH electrolytes. Intrinsically, high CO2 double as to CO with the nickel nitrogen carbide compared to AgC. She just compared the silver and the nitrogen, the all already designed a synthesized catalyst, that how it will affect the pH and how the ferritic efficiency will be affecting. Then he made she made some CO production from both up, which is dramatically decreasing in the pH2. Why? Because here and this figure we can see here the AgC and the nickel nitrogen carbide, the ferritic efficiency is increasing continuously, but when it's reached to the pH2, and the ferritic efficiency is coming towards lower. And uh, hydrogen evaluation region equity of the catalyst in acidic media, what will happen? The plate region in here, and this second figure, we can see the plate region due to the proton depletion was observed at pH 3 in both catalysts, but disappeared below pH 2, dramatically decrease in ferritic efficiency. Here's a detailed mechanism of the electrocatalytic reduction. Another one, he is a Count Smith, a Siemens Energy Germany. He was talking about that how we can improve and how we can commercialize the electrocatalytic reduction of CO2 to CO. He also synthesized a catalyst, performs as a electrocatalyst for electrochemical conversion to CO2 and CO. The main focus of his work was to convert the CO2 into CO, and then we can convert the CO to different kind of hydrocarbons. Here we can see the drastic differences in product distribution depending on the feed gas used, what kind of gas we are giving to the system, CO2. So it will be converted to CO, and then it will be make different kind of product. And if we are giving the CORR very high selectivity. So as compared to CO2, the CORR have high selectivity, field efficiency 92%, and also the current density is increased towards CO2 product. So he said that it shows excellent hydrogen evaluation reaction suppression capability, shifting selectivity towards CH4 as decreasing as we can see in the figure during the CORR 72-hour stability test. So summary of his work was the direct electrochemical reduction of CO2 to hydrocarbon should be promising initial performance, but stability is a key issue. If we are converting the CO2 directly to different kind of hydrocarbons, so it will be affect the catalyst surface. So the stability is a key issue for the ferritic efficiency. If we are going to commercialize something, so we should need to to keep in mind the basic thing that how it will be stable and how long it will can be stable. If it is more stable, so it means it will work. It is economically. Continuous work up to liquid products is required to achieve a stable electrolyte conditions. So scaling in early stages, model electrolyzer up to 5,000 centimeters square have been built for CO2 to CO reduction reaction. He is also work on this. CO2 crosswork can be managed by balance plant, and separated electrolytes require work up procedures for continuous operation and stake manufacturing similar to water. So there are some kind of challenges which we need to improve, and we need to solve this. So electrical energy input efficiency, new catalyst system for operation in acidic environment, construction of gas diffusion electrodes, and balance of plant design for stable operation. So what I have learned in this conference, CO2 conversion or electrocatalytic reduction, there are some key factors. I am thinking about that yes, material design is a very crucial role and efficiency and for the efficiency and selectivity of CO2 reduction. It will if you are designing the material, you should need to know about the material, that what kind of product I need to generate, or what kind of product I need to produce. So the material design is very crucial for this process. The second thing is electro microenvironment, as I discussed before, affect the reaction mechanism and include several sub-factors such as solvation, which means that water molecules surrounding the catalyst. And another one is water activity, as I discussed before, availability of water for reaction. So cation is also affecting the process. So different cation and electrolyte. So ion pairing interaction between an ion electrolyte, reaction plane, the surface where the reaction occurs. Region transport, movement up reactant to the catalyst surface, and transition state stabilization, how it is stabilizing the reaction intermediate. And I'm also thinking about the reactor is also have a very uh, crucial part in this to convert the CO2 into different kind of products. So we need to keep in mind that the reactor are the electrolytes. So we also consider these kind of things. And another, the parameters such as pressure is also have big contribution to this process. So we need to consider these things as well. But basically, material design electrode microenvironment is very important for this process. So thank you so much for your time and for your attention. Welcome questions.
Thank you so much, Mr. Nasir Ali Khan, for a nice presentation. And of course, you summarize almost uh, very good data from the conference and presented to the audience. And I hope it will be helpful for all of us, not only for the information, but it also is helpful. Like we have an idea, like where the work related to CO2 conversion is going to be done in different parts of the world. So of course, this was a wonderful presentation. So all of you are welcome to join us in the next sessions. That will be for questions and answers. So see you all in next session within just 5 minutes. So let's end this session here and have a very big thanks to Mr. Nasir Ali Khan for the nice presentations. And let's see you all in next seminar, next session just after 5 minutes. Thank you so much.